I just realized my mic was muted. Okay. Hi. Welcome to COMP1511's revision session. Today we'll be going over linked lists. So just make sure we're recording. Yep. Okay. How's everyone going with exam prep? All right. All right. Oof. Don't worry. We have sessions like today and the one after this to make sure you don't fail. Ideally, you won't. So make sure to listen and you should be fine. All right, does anyone have any specific questions about linked lists they'd like me to go over? Anything at all? Looping backwards. All right, that's one thing we can go over. That's okay. Hi. Pointers. Yep, I have that on my list. We'll be going over that about halfway through. All right, so the structure of today. We'll be going over what a linked list is. All right, nth nodes of the linked list. I'll make sure to write that down. Requests, nth node of a linked list, pointers, looping backwards. All right, any other requests? Nope. Okay. So, what is a linked list? Can anyone answer? Like a list that's linked. Yep, spot on. All right, but more in terms of how we represent these. Yep, it's a bunch of structs that have pointers pointing to the next one. Yep, that is a linked part. How do we actually make this? What's our struct definition? Starts with head and ends with tail. Yep. So let's actually define this in code. Need some form of struct node. Yep, so we say struct node, and then we use our curly braces. Will contain a field for data. So yep, let's just say an integer. So we say int data, and yep, a field for pointing to the next node. And like that, we've created a struct. So let's actually draw out one of these. So let's say we have a list from 1 to 3. So we just have 3 big bubbles. 1, 2, and 3. Then we have arrows between all of these. This is the start of our list. So that links to 2, 2 links to 3, and 3 links to null. All right, I'll just have to move this a little bit. There we go. All right, now why do we link to null? What is the data structure we use to represent the next one? And why will we choose null as that end value? So we can check for it. Or more specifically, as this is a pointer, that means that we need some address to hold. We can't just leave it uninitialized, because that means if we try and read this address, it can be a random bunch of stuff in memory. So we set it to null in order that we can check for it and make sure it's verifiably set to some value that isn't valid. So essentially, null in a linked list means the end. So if something is pointing to null, that means it does not exist. Therefore, we use that to say the end of it. Now, okay, let's malloc a node. How do we create this function? What do we want to return? the new node. Yep, so that means our return type is a struct node pointer. Because remember, whenever we allocate memory, we get a pointer to that allocated memory back. So we say create node, and then let's give it some data. We say int data, and inside this, let's make our new node. So we say struct node pointer new node equals malloc, and then what malloc takes in is the size in bytes. How we get the size in bytes is by saying size of, and this is a special inbuilt function that can calculate the size of anything we pass in. Wait, do you have to add like struct node head to the inputs or something? That depends on the function. So the way we're doing it really basically right now, we'll just leave it. But we can change it once we actually start building the list. So for now, let's just start off by just trying to create a node. But yes, that is valid. All right, so we say struct node. Why do we not say pointer here? Why do we leave this as just struct node instead of struct node pointer? Because you want the size of the struct, not a pointer to it. Yep. So remember, this is about pointer theory and stuff. What a pointer is a variable of the address size of a system. Mallocing new node is it just making a pointer to the create node rather than making a new node? Technically, all right, so what happens is we would return this new node. What's happening behind the scenes here is a pointer is, say, on a 64-bit system. It's 64 bits or 8 bytes long. So that means that when we just malloc a pointer, it's always going to be 8 bytes long. Let's see, how big is an integer? Well, usually that's going to be 32 bits or 4 bytes long. So what this means is if we try and just allocate a pointer size for structs, we're going to be missing out on some extra data because this is 4 bytes. This is 8 bytes. But if we just allocate the pointer, we're not going to be looking inside the struct to calculate it. We're just going to be grabbing this pointer size. So that means our memory will be technically overlapping and all sorts of messed up stuff can happen. So we say pointer so that it looks at the struct definition and calculates the size of each individual field. Because remember, a pointer is just a memory address. A memory address looks something like this. Whenever we, oh, Animankle is dancing, whoops. Whenever we just say a pointer points to a memory address, it just holds that memory address, and how we access it depends on what we want to do. So when we, yeah, so when we malloc a new node, what we're doing is if we just get rid of all this stuff, how do we get rid of it? Oh, let's just scroll down. All right. Ah. Yeah, welcome to UNSW. All right. So what happens when we malloc is, let's take a look at our system's data structure. So imagine it as like a big rectangle. What's at the top is known as our stack. This is our program's memory. Down the bottom is our data section. So that's where like all the predefined stuff like strings goes. So say we have a string that's like hello, it'll be down here. And any other global variables and stuff like that. This bit is called the heap. Now, does anyone know which bit do we malloc to? When we call malloc, where is our memory going in these 3 sections? All right, that's okay. This is technically a 1521 topic, but it really helps to understand it. So the stack is literally like a stack that you would have seen in the last tutorial, in that whenever we allocate memory, say we allocate a block of memory up here, then we allocate some here, and then we allocate some here, and we delete it off like that. And yet we allocate memory with malloc to the heap, sorry. So this is where our malloc to memory goes. So what the stack is it treats scoped variables in function calls. So whenever we call a function, it creates memory on the stack for that function call. So if we create a variable inside here called int x equals 0, what we'll have inside our main function call is x equals 0. And once main finishes, this gets deleted. So the stack is where these temporary variables that aren't malloc go. And once we reach the end of these curly braces, they are deleted. So what this means is if I just delete all this stuff, ooh, I'm accidentally moving the whole thing. Love this drawing app. Yeah, let's just forget about that now. Delete that, delete that. Say when we call our create node function, it creates a bit on the stack and it has something called new node, which points to some address. So let's say 0x1. Where this address is actually in our heap. So because we call malloc, we allocate a block of memory for our node. And this is the address 0x1. And the new node is a local variable to this, which is put in the stack. Why is it called a heap? That's a good point that I don't quite know the answer to, but basically think of like your big chunk of memory. The stack is really, really small. It's efficient, but it doesn't last forever because of the way it's designed. Whereas the heap is your big chunk of memory for everything that doesn't have to go through the CPU. It's stored directly in the RAM usually. So when we say malloc, what we're doing is we're allocating this little square of memory here and saying this can hold values, say like 12 bytes. Data is local variables. The stack is like local variables. Data is like predefined stuff when we start. So if you would say, yeah, 1521 is really fun. It goes more in depth into this stuff. This is just some helpful background for linked lists, so you don't have to remember exactly how this stuff works. But yeah, for the sake of showing you what that data section means, if we say sharp pointer string equals hello, this hello here, so I'll just move my fat head out of the way. This hello here is in data, because remember, strings are character arrays, so this information needs to be stored somewhere. And it's a constant, so it's down in the bottom here. Now, when we put stuff on the stack, so this X is on the stack here, it'll get deleted when main finishes. But when we create a node, we malloc a node. So that puts this square here, and its address of this allocated memory is 0x1. Malloc returns this to a local variable new node, which stores 0x1. And then we return new node to wherever we call this. So once this function ends, this new node here, the local reference to it will be deleted, but the memory still exists, and we'll pass back this address to our function that called it. So that's why this variable itself is deleted, but the memory has still been allocated. So that's just how it works behind the scenes. So if we now go inside here and we say struct node pointer, let's say head equals create node, one. So head will take this. I think she dances whenever I press equals. That's going to be fun. So whenever we create a new node and return the address, the local new node inside here is deleted, but since we saved the address and returned it, it will still persist outside here. If we didn't return this address, does anyone know what happens? Say we just return null. What type of leak is this known as? Starts with M. Memory leak. Yep. So whenever we have a memory leak, that means we've lost access to this pointer. So whereas before our new node points to that 0x1 we allocated with malloc, if we don't return this, we have no more variables that know this place of that address. And yes, whenever we have a memory leak, one fix is just buy more RAM, or heck, download more RAM. So can't actually do that, don't try. But a memory leak is really bad. Chrome uses a ton of memory and frequently has memory leaks. RGB adds 2 more gigabytes per stick. It may, but it's in the end, it's fancy lights and it won't protect you against memory leaks. So when we allocate this new node, if we don't return this new node, which is, remember, that 0x1 address, yep, it's equals. Okay, all right, great. So when we don't return the 0x1 address, this square is essentially lost forever. Until we terminate our program, we don't get this memory back. So let's just create this for fun. Let's just forget to return this, and all you do is we just say for int I equals 0, I is less than 1 million, or heck, go even bigger, I plus plus. So when we do this, and we create a node, we need to know for loops. Sorry, all right, so in previous iterations of 1511, people used for loops, but they generally are now encouraging a while loop. So for the sake of just showing this off, this is just an easy way for me to declare it, but it's the exact same thing as if I just said int I equals 1 million while I is, wait, I equals 1, I is less than 1 million, I plus plus. We can do it this way if it helps to explain things. Just so no one's confused, let's do that. So what we're doing here is we're calling the create node function. And what this does is it allocates memory. So say it puts another square in here each time we call it. So let's say it puts a bunch of squares on. But because we lose all the references to it, say this is 0x2, 0x3, so on and so on, these aren't what the actual addresses would be. It's just for the sake of not writing a huge bunch of letters. Because we aren't returning that address, we effectively lose all reference to it. So the computer knows that memory is there, but our program isn't accessing it because we don't actually remember what that is once this ends. So that's why we usually do return new node. But if you now say get char, so say int x equals get char, this is for the sake of demonstrating a memory leak. Let's save this. And now let's try to compile it. So dcc-o example.c. Oh, it's complaining. Scan through all memory. That's actually something that Java and C# and other managed memory languages do. They do something called garbage collection. So they take out the trash by scanning through memory that hasn't been used and just chucking it out. C doesn't do that. C is a very low-level language, so you got to take control of everything because this was made in the 1980s when computers did not have enough power to run Java. Plus, if you work on a microcontroller, it's a lot more performance intensive. So that means you need C. So C has its applications. It'll always be more performant, but it's generally less secure and harder to program for. But it's good for an intro language. So remember, whenever we want to malloc stuff, we need to include a different header. So that's our standard library. We say include send-and-lib.h. And now we compile this. Oh, and now complaining that it has a unused variable. Whoops. So let's just get rid of these. And let's just get rid of these. Just because DCC likes to protect us, but we don't need protection where we're going. All right. Semicolons, don't forget those either. And it's still complaining about that. Oh yeah, that's right. Semicolon up that. Now this should be good. All right, so if you say ./example, what this will do is it's now running forever. It's creating a ton of nodes. So if we look in memory, so let's go System, Task Manager. We see that example is taking up a lot of gigabytes of memory. Oh, it's turned yellow. That's bad. That means it's taking up a ton. Valgrind is also screaming because it doesn't know what's going wrong and why. Oh, okay, it just crashed the program. So Valgrind's got too angry and just died. So yeah, that's what happens when you create, let's see, how many bits is this? 100 million nodes and forget to free them. It'll be okay if we just say free new node, because here we still have access to the address. But we can't free these if we don't return new node, because we'll never find out where that address is. We'll just keep adding cubes to our memory. But we're not going to actually ever keep track of the addresses. So until we kill the program, we're just going to take up 3 million gigabits in the program. So I'll just put in that a get shot, and as we see, it should slowly die. If it doesn't die, that's a problem. Oh, there we go. All right. That is an example of the memory model and how we allocate stuff. So let's do this properly. So we return new node instead of return null. Instead of just creating a million nodes in a loop, we're going to do it like this. So we get rid of all this stupid stuff. And like the person said before, we now want to pass in a node just so it's easy to create our list. So let's say this is our head. And we say, we start at null. Ooh, start at null. And we give it a 1. The way we would call this now is we just say head equals, oh well, create node head 2. And this way we add it onto, oh, she's dancing again. Whoops. I think it might be a semicolon actually. All right, so when we create a node, we now want to add it onto the end of our head. How do we do this? Well, now we get into the big part of this tutorial, which is looping. So we want to now add our new node onto the ends of our list. So we have passed in a list. So we say struct node pointer head, and we want to add onto the end of this. But does anyone remember the basic structure for our loops? So we have our counter, and then our loop condition, and then how we increment a loop. So in the looping of a list, what's our counter? We can't just say I++. Struct node current equals head. Yep, that's how we do it. So we say, because we're looping over a list of pointers and a list, we need to keep track of our current node that we're on. So we use a struct node. Call it current just for the sake of nomenclature. And we start it, so remember equals means take the address of this pointer. It doesn't mean it's literally this node. It just means it's pointing at the same place. So car equals head. So if we look at our memory model, let me just draw this again. Say we've allocated a 1 for our head. So this is head. Currents. So this is pointing at 0x1. Currents will now just be looking at that same address. So current is now also looking at 0x1. It doesn't mean it's literally that node. And if we just say current equals something else, so 0x3, it'll just mean it'll now point to that place and the original node is unaffected. How we access nodes is by following along the pointer address, and that's with the arrow. So if you were to say current data equals something, say 2, that will now be following along this address. So it looks at this address, it sees that it's here, and then it modifies it inside the node. But if we're just using the pointer and just saying equals, that just changes what this local pointer variable is pointing at. So let's loop over this. What's our condition? How do we go until we reach the last node in the list? And we want the last node. So we say while current and something. When do we want to stop? Not equal to null. All right. Well, current is not equal to null. What's this going to do? Will this stop at the last node? Yep, but it is, right? We need to say, well, current next is not equal to null. Why do we say this? So it stops at the last node. Yep, so what this means is if we draw a bunch more nodes here, so say we have 2 and 3, for anyone that's a little bit stuck, yeah, it does depend on what you want to do with it. This is the easiest way outside of just storing a previous variable, which we'll get into later. But this way, say we loop over the list, we go to this one's next is not null, so we move. This one's next is not null, so we move. But 3 is the last node in the list, so that means 3 is next is null. So we stop with this loop, and then after this loop, we will be pointing at 3. So that means we have easy access to the last node in the list. So how do we increment our loop? So we know we usually say I++ for integers, but how do we loop over a list with a pointer? How do we move forwards? Yep, we say current equals current next. Now the thing some people get confused about is what this actually means. So in C, the right-hand side is evaluated before the left-hand side. So if you've done maths, that might be a little confusing because usually left comes before right. But in order for this to work, we calculate the right-hand side. So say if our current is 0x1 and we want to move to 0x2. This is just saying like the values are the address. So we say current next, we check that value. Well, the next of 1 is 2. So we store this as current equals 0x2. And then we check current, and then we just set this value to be equal to this. So now current is 0x2. I'll just move these arrows to show the point. So now current points here. Alrighty, so we've successfully moved our list. Now we want to add onto the end of it. So we have to assume this next is null. Well, why current next not equal to null, not current? Alright, so if you were to say just currents, what that would mean is we loop over the whole list, but past the end of the list, we're just going to be pointing at null. Because if our condition is not equal to null, that means that once this loop is done, this had to have been false, so current is null down here. Now that's bad because, well, we can't modify a null pointer, so this would work for something like, say, printing over a whole list or looping over a whole list. But we want to stop right at the last node. So since we want to stop at the last node and not just loop over the whole thing, that means we need to say, well, current next is not equal to null, so it will stop at 3, as 3's next is null, so that means that current here will now be node 3. And that means that we can access it here as the last node. So how do we now add this node onto the list? So we have our new node, and we have our current. How do we stitch these together? let's say we want to add a 4 here. Well, what we would do is we change the next to be, instead of null, it's now pointing at 4, right? So let's move this down. Boop. So we had to change 3 to point to our new node. So yep, Julie is right, we say currents next, so we access the next from this current equals new node. And now we have successfully added our node onto the end of this list. But remember, whenever we loop over lists, there's some considerations. So, what is the issue when we start off with an empty list? What's going to happen when we reach line 20? Because what's the value of currents if our list is empty? Null. Why is this a problem when we get to this one? Yep, Julie is right, we're accessing an uninitialized variable, or more accurately, we're trying to dereference null. So we're trying to dereference the address null, which of course doesn't exist. So we can't say nothing next. So the computer will politely die. We don't want that to happen. So we need to account for this. So if currents, or more accurately, head, is null, what do we want to do? So our list is empty. What do we want to do? Make a new node the head. Yep, so we don't say head equals new node. Why don't we do this? Because this won't do what we expect it to. If you want to make the new node the head, as in we do it like this, head equals null as the original list and 1, because we'd lose the head. Yep, Juan's right. In that discussion we had before about the stack, anything we create inside a function, remember, is copied. So this head here, it's a pointer, so we still have the same value, and we can still access pointers by the address. But the local variable called head is deleted once we reach the end of our function. So we won't have modified the list, we've just modified the argument inside this function, which will change, but it won't persist outside. That's what returns and accessing our pointers with the arrow is for. So instead of saying head equals new node, we just return the new node. So this is the only case where we loop over our head. Wait, yeah. This case, list is empty, just return new node as head. That means that if our list is empty, our new node will just be the start of the list. All right, now the ends, as we've modified this to include appending, what do we want to return as the final thing? What's going to be our head if we've added to the end of the list? Yep, it's just going to be head. So say we wanted to add 4 to this list over here. 1 is still the head, which is what was passed in. So we just say return head. Alrighty. What else do we need to keep a lookout for? Have we initialized all of our members? New node data equals data. Yep. So we need to remember to initialize everything. So when we create a new node, we need to make sure we initialize it. So you say data equals data. And yep, we also need to remember to do new node next equals null. Why we do this is because otherwise they're going to have to keep track of random functions. But this way we know that a node will just be by itself if we create it with nothing else. So okay, let's try creating these nodes and see if everything works. So we say head equals create node, and then we just say head is the head of our list. So we do head, and then we just, then we add our 1, 2, 3, and 4. All right, if you run this program, let's see We'll compile it. And it didn't crash. But this isn't very useful because, well, we can't really see the list. So let's make a function that can print a list. So this is going back onto the loop conditions and how we iterate over them. But instead of saying current next, we'll have to do something different. So okay, let's print out a list. So it'll be a void function. I'll move my head out, just gonna press enter. There we go. All right, print list. What does it take in? Well, it takes in a list. And we'll take in the head. All right. So let's assume we want to print it out just like the way it looks here. So 1, 2, 3, 4, with the little arrows between them. How do we write this? Well, we need a loop, right? So same thing as before, we need to consider what we want our loops to be. So just like before, we say struct node current starts at the head, so it takes the memory address of our head. And then we say while, what is our condition? What parts of the list do we want to go over? Do we want to go over everything? Yeah. All right, so we do want to go over everything. So we say, well, current is not equal to null. All right, now we do a printf. Let's print out our current node. So let's say %d, and then this little arrow to symbolize a list. And then what we pass in is just current data. And then just like before, we say current equals current next. All right, and let's just print out a little x just to signify null. That should be everything. Let's print out a list. So we say print list, take in the head, and we should see that hopefully our list has not exploded. Here you see 1, 2, 3, 4, x. All right, any questions about this stuff so far? Nope. All right, sweet. So now let's get into the freeing section. So what does it mean when we free memory? So if we go back into our diagram of the memory model, so we have our little sections, so our 3 tiers. This is a heap, this is a stack, this is data. What does it mean when we free this little blob of memory here? That's one of our nodes. Because we know why we free them, because we don't want memory leaks. It can be overwritten. Yep. So one of the security flaws of C is that, say we have, I don't know, let's create a linked list of all our users' information. To say we have this, and then like the password equals, I don't know, cat. So now we're storing their password in a list, and then we say, okay, we're done with this user. We've deleted this user, and we free that address. So you say that address, which is some node, which means 0x1. Free does not delete the contents of the memory because that would use up performance because it has to, well, zero out the memory. And as we know, C is all about that performance. So essentially all this does is just says, well, this memory is now no longer tied to a node. So whenever we try to call a node, that's invalid. So that would be a use after free error. And that's bad, because we don't want to use the memory after we freed it. But when we free it, it doesn't actually zero this out. So whenever we create a new node, it could just point to the same place. That's bad, because, well, we need to be careful with our memory. So if we try accessing this, we have no idea what could be in after it. They could modify this with someone else's password to say, we want to get rid of cat. Ooh. This is not smart select very well. Here we go. So say this is someone else's password dog for a different user. If we weren't using GCC, say we were using something else like a less secure compiler that doesn't detect these errors. If we were to try accessing node password, so we say node and then password, what we would actually get is this new memory, which is really insecure because that wasn't what we expected to be there. So that's why you always have to be careful and make sure not to use pointers after you free them. Because while in security instances, hell, this could be some code that someone else has written, and that will hack your program and everyone you love. So do not use nodes after you free them. Just essentially forget the pointer exists. But we do need to free them because otherwise our programs will get really fat. And no one likes a thick program. All right, so in mind of that, how do we free a list? We can't just say free head, because what that I mean is really big gigabytes equals better program. Tell that to like Cyberpunk and all the other ones. All right, say we have a list which is 1, 2, 3. What happens when we just say free head is we just get rid of the memory for 1. So this will be deleted. Uh-oh, we've lost all reference to this memory. So this will now never be able to be deleted unless we like comb through the memory ourselves, which as you can imagine, really bad, really performance heavy, and kind of not recommended. So that means that when we delete our memory, we need to loop through our list as we go through. So we go, okay, we're at this one, and we check if there's something after it, which there is. So we move our pointer there, and then delete behind us. So this way, we've already moved on, and we can then say, yep, delete this buddy. You then check, move on to this one, delete behind us, and then we check, move on to this one, and then delete. And success. Our list has been deleted. We haven't shattered any dreams or broken anyone's computers. It's all safe, and we have plenty of memory left. So let's write a function for this. So keeping in mind that we want to free the list, we don't want to return anything, so just void. And we do want to make sure we get everything. So we take in a struct node head, and then we loop over it like we expected before. So what would our condition be? Do we want to loop over every node? Say we have while current something. What's our condition? It's like what we did before is we had 1, 2, 3. Well, current is not equal to null. Yep, because we want to touch every node. We want to say, while current is not equal to null. And like before, we say, current equals current next. Okay. How do we make sure we delete behind us? Because remember is that if we just free our current node, we can't access current next anymore. because we'll have freed that memory, and that's a use after free error. So what type of variable do we need to make? We need a previous pointer or a temporary. Either way, let's do previous since that was suggested. So we say struct node pointer previous equals null. So remember, we start at null because, well, there's nothing before the head. But here we then say, well, we want to update our previous. So you say previous equals current, current equals current next. And then which one of these do we want to free? Previous. Yep. So if we just draw this out again, we'll say this. And what we have is current starts at this one. So we'll say C. P is over here. P then gets sent to C. C moves on. So C is now here. That means we've safely moved forwards in the list. That means we can just safely delete this guy. P then moves here. C moves here. Delete this dude. And so on and so on. So we just say free previous. And like that, we should have a list that does not complain when we run leak check. Let's do that. Let's do dcc -leak check. Run this, and it doesn't scream. That's great. We've successfully freed our lists. Okay. Have we done everything here? I think so. Okay. So before we go into the student requests, let's see, we're at 2:15. We're now halfway through the revision session, so let's take a little break. Just a couple minutes, go up, stretch your legs, have some water, and we'll return to some considerations of questions about how we do functions for linked lists, some recursive versus iterative methods, and then we'll go into the questions everyone asked. Are you ready? So yeah, I'll still be here. I'm just gonna grab some water real quick. I may glitch out, so don't freak out if I look weird. Alrighty, so in the meantime, until we start again in a few minutes, does anyone have any more questions? Because they'd be useful. Alright, I'll just make a little poll then. Let's see. Alright, so this little poll. Okay, so for anyone who answered that they were struggling or just have good, is there anything I can clarify that could help? Anything you're struggling with? Or just like mildly confused about? Because someone else probably has the same question. Remember, I'm anime, I'm not real, I can't judge you. Nope. Alrighty, that's fine. So we'll start up in a minute. Sit in the next session as well. Yep, so Shrey should be taking that. Don't worry, we're still going. Like this ends at 3. The next session is from 3 to 4:30. So yeah, we still have another 40, yeah, about 40 minutes left. So this is just a little break. And we'll now be going back to the questions. Yeah, this one ends at 3. I believe so. Let me just double check that. Oh wait, technically this ends at 2:30, but I can still sit here and Shrey takes over from 3 to 4:30. I'm confused about list get nth. Yep, we can do that one. Alrighty, so let's get back to doing this stuff. Who was it that said? Oh, all right, looping backwards was first. We went over pointers. Did the person who asked about pointers feel more comfortable with them now? Or was there any other questions they had about pointers? All right, this is similar to the question, the nth node of a linked list. So let's get the nth node. So I'll just close that poll. All right, so now we're going to get the nth node. So if we go back here and we just delete this little stuff, the nth node is essentially its position in the list. So this is node 1, node 2, and node 3. So let's start this off. So we want to return a struct node pointer, and we just say get nth. What we take in is the head of a list. So this starts at 1. So it starts node pointer head and int n. Well, let's just say n. This means we need to loop over our list. So what's always helpful with these questions? Remember, write down what you want to do. Loop over list, stop, end, return once we reach nth node. That's essentially what we're doing. Let's loop this over. So we say structs node currents. Alrighty. We started this at head. What would our condition be? Well, we do want to loop over the whole list, remember? So that means we need to say current is not equal to null. Okay. We do want to say current equals current next. Let's move my head out. We need an int incrementer. Why do we need that? What does the int increment do? Because, well, we can't really keep track of what node we're on with current. We just know the node, but we don't know the position. So if we say int current position equals 1, that means that whatever node we're at is that one. So if we say current position plus plus, that'll mean that we'll increment whenever we do this. So okay, current is not equal to null, so that means this node is valid. How do we check that we're at the nth node? Is it bad style if we use I instead of current pos? Kind of. It depends. It's a little bit more obvious than a regular while loop, but current pos, you always want to go with the variable name that gives the most information. I is technically acceptable, but I say current position makes more sense immediately. But yeah, I is still valid. Alrighty. How do we check that we are at the nth node? Current pos is, wait, current pos equal to 0. Remember is that we want to say current pos starts at 1, because the first node is 1, second node is 2, because they're going from nth. Let's say linked list start at 1, but array is still start at 0. It depends on your personal preference. So current position, like Julia says, is equal to. If we say n, that'll actually reset current position to be that value, which is not what we want, because that'll always be true, because the result of an equals is true. So current position equals n. Things then they'll tell us to counting the list, right? Yeah, they should. And if it's not clarified, always send an email. They're usually pretty quick. But yeah, you communicate with emails in the exam. So current position is n. So what we want to do is we just return current. And this way we have found current. Okay, what do we want to return if we didn't find this? Say we put in 5. What do we want to return? So we finished this loop. We didn't find a node. Null. Yep. So it's an easy way to say, if it's not in the list, it will just be null. This works for an empty list, and this works for any other list that we throw at it. Alrighty. For the person that asked about that, how do you feel about getEnth now? How about int function? So you mean instead of returning the node pointer, return an int like this? Yeah. All right, so if we're going to return an int, what that means is we no longer going to return the pointer. What will we just return? So we want to return the data from the nth node, so we just say current and then current data, yeah. Current data. But now we can't return null. So this is one of the drawbacks of getEnth, is since we're returning an integer now and not a pointer, we don't have an easy null value. So you usually have to define like what an invalid number is. To say, can we return 0? Well, it depends. Because what if you just have a list of 0? Like say if I want to return, this is 0, this is 1, this is 0. We have a binary linked list. This is technically a valid linked list, but we'd have to define it and say, no, you can't use zeros if you want to do that. This is the difficulty of just returning an integer and not a pointer, because we have to define something outside of the language context to say what is valid and what it isn't. And it's up to the person using the code to do that. Because if they get it wrong, well, suddenly a list which should have been invalid is now valid, and a list which should have been valid is now invalid. So let's say we define this cannot have zeros as 0 is code or not found. There's a bunch of defines we could use, but let's say 0 like we said. In this case, we just return 0 down here and put in the restriction that no one using lists with this function can have 0 in them. But yeah, again, this is not preferred because, well, it's kind of gross. The other way we can do it is just crashing the program if they put in a list which doesn't have it. Naturally, that's bad. I use return code data twice. All right, why would you use code data twice? So you mean this would be code data. Why would this not work? Take a look at the loop and think, what will current be at line 80? Current will be null. And remember, we can't access a null, so we can't look at a null pointer and then try and dereference it with the arrow. So this will result in a program crash. And that's technically undefined behavior, which we don't want. So don't dereference null pointers. It's better to just say 0, because otherwise, while current next is not equal to null, but in that case, you're just going to be returning the last node in the list, because that's a different kind of behavior. So again, that's something we have to define. So if we choose to do it that way, we're trying to get the nth node in the list. So say we do 1, 2, 3. If we say 2, then we get this one. So if we say pass in 4, if we return 0, that means 4 was not found. The fourth node was not found in the list. Or another type of behavior is we just return the last node in the list, so the one closest to the number. So if we do that instead, so we say current next is not equal to null, we just return current dot. What I did was make, well, current next is start off by going next and then check. You could technically do that. But what this does is now, instead of having the list cannot have zeros as code for not found, we have to say if n is greater than length of list, last node is returned. So it's all about defining different ways of doing this. All right, current is not equal to null and current pos is less than n. That's one way to do it, but that has the same result. So if we say current pos is less than n, that means that if, let's say, current pos just reaches, well, current pos will always be less than n, or well, less than or equal to. So what happens is if n is 5, confused about return here, which return? 75 or 81? 81. Alrighty. So while we're saying current next is not equal to null. So that means that current, so we've looped through the list, we've gone current is this one, then it's this one, then it's this one. But since 3's next is null, that means we end the while loop here. So that means current equals 3 as current next is null. So when we just return current data, that means that we just return the last node in the list. All of these decisions here are essentially workarounds because they return the same value. Not quite. Because remember what happens if our list is, we reach the end of the list without finding the position. So say we pass in position 80, to say position 80. What this will do is current position plus plus, current position plus plus, current position plus plus. This will trigger because we've reached 3. And it doesn't matter what we say. Oh, no problem, Julia. It doesn't matter what we say for the size of the list and less than n or anything, because we'd have to loop over the whole list anyway. We can't go to position 80 with this list as there's only 3 nodes. Hey Brandon, welcome to the session. We're just about finished, by the way. But don't worry, we'll still be finished in here. So what this returning here does is it returns the current data if it's equal to n. But once we reach the end here, we can't just return current data if we just say current, because current will be null once we finish the loop. So that means we had 1, 2, and 3. And from here, if we tried to loop to n equals 80, well, we're going to reach null before you reach 80. So n will be equal to 3. We will never reach 80. So n will always, current position will always be less than n. So that means that we have to either say, well, current next is not equal to null in order to preserve the data and just return that last. Or we define some value that is invalid. So we say not found, and we hash to find that or something. So yeah, there's different ways to implement this. This one is if we have found it, but past this loop is if we haven't found it. So past here, have not found the nth node. This usually means our list was too small for that n. Does that make more sense? Yep, sweet. Alrighty, and the last question that we had that was defined was looping backwards. Alright, so this is a slightly difficult one. So why is this difficult? Well, we technically can't do this with a normal linked list. So why can't we do this with a normal linked list? So say we just have this, which is 1, 2, and 3, and then connected like this with each next equaling this one. Say we have our tail pointer. Why can't we go backwards this way? There's no pointer to the prev node. Yep, so that means we'd have to implement what's known as a doubly linked list. So that's what happens when we say struct node next as well as struct node pointer previous. Now there's a bunch of issues with this in that it's a lot more complicated to do doubly linked lists, as we would need a really good reason for them, and we need to consider this every time we do an operation. So that means functions become more complicated. So we say, now new nodes, remember to set new node next. Well, sorry, new node previous. This made Pokédex not fun. Yeah, previous is always more complicated. The alternative is just looping over to the previous node each time, but this is more performant, it's just really hard to write. So you say previous equals null. We need to remember to modify the previous in every function. That's really, really annoying. So now when we create our head, it starts off as null. If head is null, we can still just return the new node. But now we have new considerations for this. So now we loop over to the last node in the list. So current equals the last node in the list. If we're adding our new node onto the end, that means we also need to remember to set new node previous equals current. See, it's a lot more complicated because, well, we have essentially twice as many places to make a mistake. So only do this if it's absolutely necessary. So we say current next equals new node, and then we need to remember to set the previous. So say we are adding, if we just get rid of this stuff. So we add 3 onto this, we create our new node. This was our last node in the list, so we connect that to 3. But then we need to remember to connect 3 back to 2 when we add it. And let's just assume these two are connected as well. So naturally, this creates a bunch of problems in that we need to remember to do this for every single operation. But now that we have done it, let's say we just have a loop of the list. So we can just say, let's see. For the sake of just grabbing this last node, we'll say struct node pointed tail equals create node. Oh wait, no, it won't have that, will it? Yeah, we still have to say head. But we now need to loop over to the end of the list. The way we loop over to the back, so let's use this get nth function. So we'll change it back to struct node pointer. Struct node pointer get nth, and this way we just return current, otherwise we return null. This is thankfully going to cut down some time for this. So we're just returning the pointer at the nth position on our list, starting at 1. So now we just get our pointer, so we say struct node tail equals get nth from the head, and we want the 4th node. All right, And now we want to loop backwards. Let's just do it inside our function. How do we loop backwards from this tail? Well, we still need a current, right? So we say struct node pointer current, but what are we starting at? Are we starting at the tail or the head? Tail. Yep. So since we want to start from the tail, so remember it's like a snake. It's like a little hissy boy. This little tongue, and that's his cute little tail. We want to start at the tail, which is at the back. But now, what's our loop condition? We had to think about this. Well, current is not equal to head. Technically, maybe. That's one possible way we could do it. But what that means is at the end of the loop, our current will be head. How do we even loop backwards? Well, that's what we're going to be going through right now. So we can do it Bodie's way. So we say current not equal to head. Current not equal to tail wouldn't work because, well, we're starting at tail. So that means our loop would never run. So we want to reach and we want to go back through every node. So you want to loop backwards and finally reach null here. Because remember, the previous of the first node in the list is null. So we still want to say, well, current is not equal to null, but this time we're not going forwards, we're going backwards. So, okay, how do we increment this? Current equals current previous. Yep. In this case, does each node have a pointer to the previous node? Yeah, if you missed that as we did it, we added a previous and modified our create node function to stitch it to the previous. Remember, this is complicated. You essentially cannot loop backwards through a list if you are doing it from the backwards. Wondering how to loop backwards without a previous node. Oh, yeah, that's really hard, but I can show you how to do that. So current, previous. This is how you do it in a doubly linked list. So we move ahead. Here we see current equals current previous, and then we'll loop backwards. And yes, we can do it that way. So if you want to loop back without the previous pointers, let's say we have the head. Yep, so we need the head. So we want to loop backwards. So what this will do is if we want to loop backwards without previous pointers, so let's just ignore these. So say we want to do a print backwards function. So let's do that. So let's say void print backwards. And we need to take in a head, struct node pointer head, and we go backwards like this. So what we do is a little annoying. So we need to say struct node pointer current, and we want to essentially just keep going back. But we can't do this very easily iteratively. We do something known as recursive programming. So, recursive functions, if you remember them from week 10, we have what's known as a base case. That means when we want to stop. So base case means when we want to stop. And then we have our recursive portion, and then we either do something before or do something after. So we want to consider this. So we still call these forward. So we call this on the struct node head. So say we call this on 1 first. So call on 1, call on 2, call on 3, and so on and so on. But we can choose whether we want to operate on it before we do the call to the next function or after we do the call. So a base case, in pretty much the same way as every other linked list thing, when do we want to stop when we are going over a list? If our head is equal to same thing as all our loops and everything, we need to say null. If head is null, we just return. We don't want to do anything special. But say we have something after. What we do is we do print backwards, and then we need to pass in the next node in the list. So we say head next. And so what this will do is head will now be 1, head will now be 2, head will now be 3 in each of these calls. So think of this like all indented forwards after each other. So we call on 1 first, which calls on 2, which calls on 3. And depending on whether we do something before the recursive function or after it depends on how we do it forwards or backwards. So if we print backwards, that means we want to do our call after. So that means we say printf here instead. So you say %d, and then the arrow, and then we pass in head starter. Because if we put our printf before the recursion, that means we will print 1 and then call the next one, and then print 2 and so on. But if we do this, that means we print 3 first, as that's the last thing here, then we go back and print 2, then we go back and print 1. So let's just test this to make sure that we have it correct. So this is how we loop over backwards, is almost always with recursion for the sake of just not running so much code. So let's just comment out this section. Now let's print backwards. Prints backwards of head. And we should see if we coded this correctly. Unused variable, that's fine. Yep, we see 4, 3, 2, 1. Now why this works? Well, let's do some helpful printf statements to show. So new call of print backwards, head equals, and then we'll give it head star. This will allow us to visualize how we are calling these. So if we run this through, all right, it has to be not equal to null. Have to do this. Yeah, I have to move this downwards because if head is null, we can't print out the data from it because we would do referencing a null pointer. So we just do our print out here, and then we say /n, and then we go, what was it? This one. All right, now this should show the calls a little better. Here we see new call of print backwards. Head is 1, head is 2, head is 3, head is 4. This one was null, so I'll just do a little printf to show that a little better. This is how we do this without a previous pointer. So we use recursion. And recursion is really powerful because it can do all sorts of stuff like this, where we either choose to do something before we call the recursion or after we call the recursion, and we can combine values from it. Since we just want to print, it means that it'll run all of these new calls first. So we go into a new call with head equals 1, it checks if head is null, it then runs the next one, so it doesn't run this printf until it returns through from all the next functions. So we run it with head next. That means head is 2 here. It runs through the same thing, but again, it doesn't reach the printf until after the next ones it calls returns. It calls 3, does the same thing, which then calls head equals 4, which does the same thing, except now head is null. So we finished our little debug info here, and we just return. So since we've returned, that means that we'll now go back to this point here. So we've finished this print backwards here when we called it from head equals 4. So we then print the current node, which is 4, so the last node in the list. Once we reach the end of these, that means we return. So that means we go back up to head equals 3 here, and then we call 3 and the arrow. We return again. We're back up to head equals 2. back at this point inside head equals 2. We then print out 2, return, back to head equals 1 at this point, and then we print 1, and then we are finished. Does that make more sense? This is how you do recursive functions and how we print out something backwards, or essentially the same process can be done to anything looping backwards without keeping track of our previous pointers like we did here. Oh, there. All right, and just to show you that this does pretty much the exact same thing, is if we put our recursion before if we put our something before the recursion, it will print out the normal order. If we just do this, we'll see it just does, oh, where was it? I think it's disappeared. Oh yeah, we'll have to get rid of these. There we go. So just so it doesn't show the things anymore, we're still recursing over, but we're just calling each one as we go through and make our function calls instead of after we return from our function calls. So remember, you do this if you want to do something before you go down the list. You do this after the recursion if you want to do something at the back of the list. Does that make sense? So if you move this down, we should see that it goes back to being inverted. Yep, like we drew out before and went through all of those instances. We go from the back, it returns the next one. 3, it returns, it goes back to 2. It returns, we go back to 1. Does that help for the person who wanted to know how we loop backwards? Here's the full function. Yay or nay? Spend some more time with recursion. Yep, so the best thing to do with recursion is try doing those week 10 tutorial exercises. They're really useful, and I would suggest that you do them because, well, they're nice to know. Recursion is a handy tool, because this would be really bad to look at if you were doing it with iteration. But since we can do recursion, all we need to define is a base case, so when we want to stop, and then we either do something before we call the next set of functions, or we do something after we've called every set and then work our way backwards. So yeah, it's basically whether you want to do something on the way down the function calls or on the way back up from the function calls. And yeah, all this is doing is essentially just looping over the list, but instead of looping iteratively, we are looping recursively. Is there any final questions? Because we still have a couple minutes before Shrey comes on. Anything at all? No. All right, let's make an, ooh. Don't have any more questions. Sweet. All right, let me just get up a poll. All right, let me know how this went. Going for the pause in math 1, 2, 3, 1. Yeah, it's a little. Math was never my strong suit either. I'd say a HT is achievable in comp. Not so much math, but comp is achievable. Good luck, guys. I'm sure you'll do great. Alrighty, so in about 10 minutes from now, Shrey will be doing the next section of the linked list parts. I believe he'll be mainly going about like modifying lists. So this one was for all the whatchamacallits, all the iterating and all the like the basic stuff. But I hope that's now a solid foundation for everyone. Take a little break, stretch your legs, and I wish you all luck. It's lovely teaching you guys, and I'll see you around. Okay, bye.